right, we're live again. Whoopsie. Yeah. So now I guess Nancy, I'm sorry, Nancy. I guess you're gonna have to delete the other one, and yeah, yeah. So we're gonna need a new live stream for 584 because I messed that up so badly. I'm gonna blame YouTube though because it put the live streams in the wrong order for me. So yeah.
I'm okay with that.
YouTube putting live streams in the wrong order? I'm not.
No, blaming YouTube. I'm okay with
Blaming
blaming
YouTube.
YouTube.
Yeah. Have you heard the nightmare that's going on for people who are using Twitch? The all of
Yes, all
the
the DMCA
Yeah.
calls.
But it's funny. Like again, back to being a pro, right? Do you play copyrighted music in any way, shape, or form ever on anything that you do ever?
No.
No. Come on. Really?
So for those of you who don't know what's going on, Twitch had been letting people get away with stuff
Mm-hmm.
in a way that made those creatives feel that Twitch was cool with what they were doing.
Yeah, that they were
And
safe.
then and then the publishers of the different copyrighted material went after Twitch.
Mm-hmm.
And Twitch was like, oh, oh, people are going to come after us.
Yeah.
And so they sent out to a bunch of their creatives a notice that somewhere in their however many files, there was something that triggered a copyright alert without saying what it
Yeah.
was. And they're requiring the creatives to pull every clip, every VOD,
Yeah.
every highlight for however
It's
many
it's
years.
worse than that. They just deleted a bunch of stuff. So Twitch just went and
Mm.
just deleted a bunch of content.
They did give a bunch of partners 4 days to pull everything.
Right, but from what I understand, they also just deleted stuff. Maybe it was just the
Damn.
clips. Maybe it was just clips because you could pull a clip out of a larger video,
Yeah.
like a VOD. But still, yeah, yeah. Like I just I can't believe that. I mean, and so people just thought like, oh, Twitch is so much better than YouTube because on YouTube, YouTube, you're constantly getting these copyright takedown requests,
Right.
and we're at the point now with YouTube where we're hammering out the fine-tune issues of the copyright, like
Hmm.
when there's a copyright takedown, what happens to the income, what is the method for counterclaiming, and for YouTube didn't used to tell you exactly where it was and what they were claiming, and now YouTube does. So YouTube's copyright system, and in fact we even have the ability to check other people using our copyright, which we don't care,
Right.
but still we can if we wanted to. And Twitch was just the Wild West, and I just looked at that as people were just playing music, just playing top 40 while they were doing a live stream, and you just knew what was going to happen.
I I thought that more people would be okay because Twitch is for the most part ephemeral content.
Mm-hmm. Mm-hmm.
But if you're a partner, they keep your VODs. The rest of us stuff is gone in like 30
Yeah.
days.
Yeah. Yeah.
So, yeah,
Yeah.
we're
And
fine.
yeah, and I mean the long game of this is the exact same thing of what happens with video games, right? Like video games
Yeah.
are essentially copyright infringement. When you play a video game and it has the music and you're playing it on your Twitch stream, you are infringing the copyright of the copyright owner, the video game creator. And they can, if they want, like Nintendo, drop the hammer. And some people don't like you like just playing the whole video games to show the ending off. But the and the only reason it works is because all of the content, all of the video game providers turn a blind eye to it, which is not a great way to create a sustainable platform, right?
Well, I think they understand that a lot of these Twitch streamers are also essentially advertisers
Yes.
for them.
Oh yeah, yeah. And again, and that's the full circle is that the
Yeah.
music companies are absolutely cutting off their future
Yes.
because what they're doing is they're going to make sure that every place that young people get access to music today
Mm-hmm.
is a place that is completely safe for copyright. And so you're seeing on
Right.
Spotify there are copyright clean, copyright safe music streams that are pretty good that people are now playing in the
Yeah.
backgrounds of Twitch. And so people aren't going to find out about the music from the big labels. And not only that, but everybody is going to be so angry that when the
Mm-hmm.
big labels come around, they go, "Oh, we're so sorry. Yeah, you can play our music." No one's going to trust them. So they have completely
Yeah.
shut down the future of promotion of their stuff. All right.
And now is not the time to be pulling the stuff because like
Yeah.
print publishers, I don't know if you've seen this, but most of the main publishing houses have said that their work through at least the end of the year, if not beyond, because of COVID, is completely free to read aloud.
Hmm.
And you better believe I'm totally taking
Yeah.
advantage of that.
Yeah. That's fantastic.
Uh,
Yeah. Yeah.
that's what you do.
Yeah. A
And then
lot of
people
people.
remember you with reverence.
Yeah, the New York Times has made most of its COVID reporting freely available. Like it's a
Yeah.
difficult time. People need access to content. They also are having difficulty paying the bills. Now's the
Yes.
time to show that you're there to help support. So I'm going to say hello to some people. Hello to Ben Kalo, Beth Johnson, Iskolax, Genghis Galahad, George, Graham W., Giddy Bieber, Helg Bierkog, Hugo Burnham, Katrina, Astro YYZ, Larry Beckham, Linda Sadiq, Nancy Gazzino, Paul Disney, Paul Gracie, Rich 901, Roman Gibber, and Thomas Tranneker. And maybe people had said hello earlier, and I apologize.
And I'm going
Um,
to say hello to the folks who've said something over on Twitch. So, hello to Commander Unifix. Hello, DPI209. Hello, Wayne Johnson. A Middles. Adam altogether. Null denominator. Um, hello, A McMullen. And I think I got everyone over on Twitch.
awesome.
Hello, all of you.
Sorry for the for the mix up at the very beginning there. I hope people have stuck around. But yeah, anyway, just latest craziness in the Twitch in the world of being in new media.
Yeah.
Yeah, it's
Every day is a new day.
yeah, yeah. I again, we are so careful. It's funny. Before we get onto the show, we're so careful about
Yeah.
copyright in the videos that we do on my YouTube channel that Chad refuses. Like I'm the one who's like, it'll be fine, and Chad's like, no, it's not. Nope. No, like, do you have permission in writing? Hi, Rich Wilson, to use that picture. I'm like, it's fine. And he's like, nope, find something else. Come on, Chad. Just let me
Yeah.
skirt the gray areas of this. And
I
he's been really good.
I spent the summer of 2007 reading through the Digital Millennium Copyright Act and documents that would allow me to understand the stuff I didn't understand when I initially read it. And that painful, painful summer has served me well.
Yeah, yeah, yeah. No, I mean we've had to deal with it, and I've even gotten I've gotten punished. There's been times because we have writers who pick pictures and they put them in their story, and
Yes.
so I have all these little time bombs hidden all through Universe Today that occasionally they reveal themselves and I have to swap out a picture and we're always looking and so we call that using pictures we have unforgivable curses in Universe Today for the team. And so there's a bunch of stuff where I'm like I turn a blind eye to, and there's a few things that if you do and I find out, you never get to work with us again. And
I have done that to somebody.
yeah,
Yeah.
yeah, yeah. I'm just like that's unacceptable. You know better. And
Yeah.
one is, is plagiarization. Like,
Hmm.
like there are making stuff up, plagiarizing, and using other people's content without their permission. Those are
Yeah.
the Cruciatus killing curse and I forget the other one in Harry Potter. So here, anti-gravity nonsense says that Chad and Fraser should just play and sing their own background music. Yeah, exactly. Anyway,
We know
copyright.
people like David Joseph Wesley. We like David Joseph
Oh
Wesley.
yeah, yeah, yeah.
I
No,
like that idea of turning to these amazing people we know much more than
yeah.
the idea of Fraser singing.
Yeah, we did an episode on our channel, which was just as an experiment because David had done some amazing music to celebrate Cassini, and so
Yeah.
we did a video with
That was
his
gorgeous.
music, and it was wonderful,
Yeah.
and it was a great collaboration between a musician and us. It took a lot of work though, and even we had to negotiate his label's permission, and I got copyright takedown request that I had to battle to just make
Oh,
that video function. And that was with full permission, written permission from the creator. So it's like, it's a tricky world out there to try and navigate. Anyway,
yeah.
man, I know people just love going down the copyright rabbit hole, but I guess we should do an episode, which,
We
by the
probably
way,
should.
we allow you to use for any purpose whatsoever.
Everything we do is under a Creative Commons license.
There you go.
Just give us attribution.
Yeah.
We kind of like that.
Yeah, just let people know where you got it from. But yeah, if you want to mix this into some musical work that you're doing, which people have, or some art exhibit, or
Yes.
if you want to show this off on your television station, if you want to release this as part of your podcast as a clip that you're doing, if you want to use us to whatever, feel free. That's how we roll.
I have habits of saying certain phrases that people have cobbled together into the most ridiculous videos.
Yes, that's funny. All right, let's move on to recording an episode of Astronomy Cast, because apparently that's a thing that we do.
It, yeah, I think so.
All right,
This is episode 583.
583. Yeah.
Okay. And remember to do it 16-bit.
Not 32-bit?
Yeah, that's what Rich said.
Hmm. I'm going to sneeze at some point. Maybe not.
Okay. I am all set.
Okay, I'm going to press record.
Okay. I have pressed record.
Great. Okay, wait a second. Hold on. So he wants 32-bit float?
No, he wants 16-bit.
He wants 16-bit float.
Yes.
He can mix it. He can figure it out. Because I use 32-bit for everything. Oh.
I know, I do too.
Yeah.
I do too.
Because he's just worried about file size. Richard, can
Yeah.
you tell us why you want the 16-bit versus 32-bit? Because if it's file size, like we'll upgrade your Dropbox account or something.
No. Apparently, he went through and every episode of Astronomy Cast we've ever released, we've released it 16-bit.
Yeah, but you want the highest quality raw audio first, right? And then you down mix it to 16-bit.
That's what I thought.
Yeah. So, Rich, I'm going to record at 32-bit just because, otherwise it'll mess up my process. But can you let us know why, and then we can fix it? Okay, I'm going to stop this recording and start again.
Okay, I will do the same.
Unless
okay.
he doesn't watch the... Maybe we should. All right. Okay.
I'm
tell me if it's
pressing
record.
return.
Record? Okay.
Yep.
Hi, Richard. Fraser here. You asked us to record in 16-bit, but I am going to record in 32-bit. Can you let us know why? Because is it because you don't have room in your Dropbox? Is it because you like the quality of lower quality audio? Too processor intensive? Can you let us know the reason? All right, here we go. Because it seems weird to me. Astronomy Cast, episode 583, the 2020 Nobel Prize in Physics. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. I'm Fraser Cain, publisher of Universe Today. With me, as always, is Dr. Pamela Gay, a senior scientist for the Planetary Science Institute and the director of CosmoQuest. Hey, Pamela, how you doing?
I'm doing well. How are you doing, Fraser?
I am doing great. I'm sure all of you were just absolutely glued to the television just a couple of days ago watching the OSIRIS-REx landing. I know you did a big live stream of it.
Yes.
Absolutely amazing to see the sample collection.
I am eagerly awaiting the spin maneuver during which they'll use the spacecraft's moment of inertia to
Yes.
figure out how much material they vacuumed up. And then we know if they go and try to do this a second time, or if they just head on home.
Yeah. Yeah. Absolutely incredible. So for people who like you watched it, you watched the simulation of what it was supposed to look like, and then later on you got this animation of it actually doing the capture, and it looked identical. And then suddenly, poof, there's this big cloud of debris as the spacecraft is gathering the sample and then popping back into space. It was absolutely amazing to see it, and just to think full circle that we were there to watch the rocket launch, and now we watch the sample get collected, and hopefully
Yes.
we'll get a chance to watch it. And so they're going to spin up the spacecraft, uh, be able to detect the amount of material that's collected into the spacecraft, and then from that point on, they'll know whether they have to try again or whether they're good to go, and they're just going to be able to return home. So it's yeah, it's pretty incredible.
What is most amazing to me about this, just to add one more thing on this day of going sideways, uh, they planned the mission so that when they went down to the surface, they'd be using their laser altimeter to figure out where they were relative to the surface. But this surface is such a boulder strewn rocky mess
Yeah,
that they instead had to do image matching on the way down. So they completely changed how their navigation works. And it's because they were making sure, okay, does what we're looking at match what it should look like?
yeah,
That it looked just like the simulations.
yeah.
They
It,
essentially recreated the simulations one image at a
yeah,
time.
it just shows the level of care that they went into to make sure that this went right. Yeah, absolutely stunning. All right, well, let's get on to this episode, which has absolutely nothing to do with Osiris Rex, but maybe we'll be talking about that next week. So, this year's Nobel Prize in Physics was awarded to three brilliant researchers who worked out some of the secrets of black holes. Today, we're going to talk about the chain of discoveries that led to this award. All right, Pamela, where do you want to start with this year's Nobel Prize?
I think starting with Penrose is probably the best place to
Okay,
start.
let's do it.
So the prize was split in half and then in half again. The first half of it went to Roger Penrose, who I kind of adore as someone who thinks geometrically. This is somebody who figured out uh, how to create what's called the Penrose triangle, which is a way of drawing a Escher-esque style triangle that can't physically exist but looks three-dimensional when you glance at it quickly. And his work was actually inspired by Escher. And then he went on to figure out how to make staircases that are going both up and down simultaneously, and shared what he was doing with Escher,
Mm-hmm.
who then incorporated it into his art. And it's this amazing way of thinking multidimensionally that I think allowed Penrose to look at four-dimensional space-time in all of its crazy warpage under the influence of relativity and see his way through to being the first person to mathematically describe how black holes can exist. Einstein had seen in his math that black holes could be the fallout of what he had created, but declared them aphysical, not something that
Right.
should exist. And Penrose came along and was like, no, no, no. Okay, here, let me change how we discuss the mathematics of this by using a topology argument. And his paper that made it clear black holes can exist, that's an awesome result. But what was much more powerful is he opened up a new way to discuss relativity through topology.
I think it's really interesting. Like when we report on various black hole discoveries and we talk about how Einstein was right again as it relates to black holes and with the Event Horizon Telescope and things like that, the reality is that Einstein didn't put a lot of thought into the implications of his theories as they related to black holes, as you say.
Yes.
He worked out in excruciating detail the way time and space are intertwined and acceleration and how light and time should work near gravitational wells and so on. But
Yeah.
to practically think about the implications and come up with this idea of black holes was a lot of researchers after him who took that work and ran with it.
And Penrose is considered to have been the first and most important follow on work to relativity, to have extended it in directions that essentially opened up a lot of the modern understanding we have of the universe. Now, the problem is that you can mathematically describe a black hole all day long,
Mm-hmm.
but until we can detect it, all it is beautiful equations. And unlike string theory, this is actually beautiful. And Penrose, along with Hawking's and several others, have fallen prey to the we did some really cool research, but it hasn't been observed yet. And unfortunately Hawking's had passed away, but Penrose is still out there, still working as a faculty member out in Pennsylvania. And so he was still here to get a prize for work that he did before either of us were born.
I wonder what if Hawking had lived, would he and Penrose have shared the Nobel Prize, and then it would have been shared with someone from the experimenter team? I
I
wonder.
don't think so because Hawking's work was on the evaporation
Mm-hmm.
of black holes, which this doesn't speak to.
No, it's true. It's
This
true.
Hawking was actually he worked as a student with Penrose at one
Right.
point.
Right. Yeah.
So they were peers and collaborators where Penrose was the senior collaborator.
Yeah. Oh, that's my intro. So okay. So Penrose. I mean, one of the names, one of the things when I think about Penrose, I think about the Penrose process. This idea that you could extract energy from a black hole. I mean, he has a lot of interesting ideas, a lot of way out there ideas.
Yes.
Some are theoretical. You know, he has big opinions about the cyclical nature of the universe, which
Yes.
will get him into vociferous arguments with a lot of other cosmologists who deeply
I'm
disagree with
okay
them.
with those arguments. Well, and this is the thing that makes the theorists the Nobel Prizes in some ways so much more interesting. You see the same thing with the Nobel Prize that went to the original observation of the cosmic microwave background. The theorist kind of got left out to the side, but had done so much more interesting stuff. And here it was the observers that got the prize for noticing that the theory was right. Well, with Penrose, I'm so grateful that they included him in this. And and with what he did, he changed fundamentally how we look at black holes initially. And then he took his topography modelings, he took his what matters is the flow of space and time more than the details of all the connections through that topography. And by changing how we look at things, just like Einstein changed our understanding of space time by curving space, Penrose changed our ability to articulate that by saying, let's look at the surface of that space time and trace out the geodesics. It was a revolution in thinking. And from that, we just kept seeing new and interesting things fall out. And I love that what we're seeing with both of these men, Einstein and Penrose, is that by looking at the universe geometrically, it radically changes our understanding from simply working equations, which is what we teach kids to do in school. Imagine how much easier it would be to understand our universe if we instead looked at the flows of information instead of the equations of the information.
Yeah, yeah. Um, Geometry is one of those mathematics that I have a fondness for. I mean, when we learn geometry, even in like grade 8, and we start to
Yeah.
see how you can make these calculations and how the whole thing, as long as one part works, then you can work out like a Sudoku puzzle the rest of the angles in in your series of triangles and shapes and all that kind of stuff, and all of these ideas, and then they extend into other dimensions and other, other kinds of shapes, and and yet at the end of the day, you're working with shapes and topography, and it's kind of fascinating to think that even some of the most complicated objects in the universe, these black holes, which are spinning and twisting up space time around them, still allow the tools, exploration with the tools of geometry to
And
figure
with
out how they behave.
the Penrose process, Penrose energy, what's amazing is how this is fundamentally still getting used every day. This very week, we had a new article come out talking about how it's been determined that our galaxy supermassive black hole can't be rotating that quickly because it isn't injecting energy into the orbiting stars around it.
Yeah.
Our ability to figure out we have a slow rotating black hole through decades of literature derives from this whole Penrose process. And so this is physics is now so fundamental to everything we do that the release we looked at didn't even relate it back to this. It related it just to relativity. It's just part
Right.
of
Right.
relativity. And
Right. Right.
unfortunately, Einstein's the only one who really gets credit for relativity.
So let's talk about that idea of the Penrose process just briefly before we move on to the other parts of the Nobel Prize.
So the basic idea is that when you have a rotating black hole, it's able to spin the space time around it. And as that works, the spinning can get carried out outside of the event horizon of the black hole. And because this dragging of space time extends beyond the event horizon, it essentially can insert energy into the universe around it. Now, I have to admit, the way my brain conceives of it is that you simply have a continuum of there's a rotating black hole in the center. Everything around it is twisting with space time. And somewhere within this continuum of space that's twisting is where the event horizon lands.
Right.
And it's that twisting of space time that makes such a mess of things, but also allows us, when we're looking at accretion disks in other galaxies, when we're looking at the orbits of stars in our own galaxy, to get at that rotation rate of the black hole that we otherwise could never get to.
Yeah.
It also makes the math a whole lot uglier. Even in graduate school, most of the time when you're doing the maths, they tell you to assume a non-rotating black hole because they show a small
Right.
modicum of kindness.
Right. Right. All right. Well, let's move on to the from Penrose's work on the theoretical implications of black holes to the experimenters and observers that actually found them.
And this is one of those things where I have to start by saying I spoke quite highly of Reinhard Genzel as simply being a nice human, and most of the time he is. But right after I said that in our last podcast, he said something that I just want to call out as, dude, not cool. So Reinhard Genzel, along with Eckhart, who was first author on the paper back in 1996, were the first to use speckle photometry. This is where you do extremely high speed imaging, and then you shift your images around on the bright spots in the image to line those up so that you could take out the effects of the atmosphere. He was the first person to use speckle imaging to look at the center of our galaxy and identify the motions of the stars closest to the black hole. This paper came out in 1996. Andrea Getz followed up as first author on the paper she put out in 1998. Genzel's team was using the New Technology Telescope from the European Southern Observatory. Getz was using the Keck Telescope in Hawaii. Same kinds of measurements from both teams. And since 96 and 98, they've been both working in competing teams, with Genzel taking leadership of his team, going back and forth, increasing our understanding of the supermassive black hole in the center of our galaxy. So Genzel's paper was first. He was not first author on it.
Right. Okay.
And
So let's talk just briefly here about why these observations were so difficult. I mean, you talk about this idea of speckling, but I mean, the place they were looking is a place that one is not has had not been able to look, and that's the key.
so, so they were dealing with two major difficulties. The first is between us and Sag A star, that source of weird energy in the center of our galaxy in the constellation Sagittarius. Between us and there is a whole lot of dust, a whole lot of gas, which makes it impossible to see all the way to the distance of the center of our galaxy using an optical telescope.
Right.
Now,
It is the
luckily,
zone of avoidance.
yeah. And something that is completely opaque in optical wavelengths can still be transparent in other wavelengths. In this case, they were using 2.2 micron infrared radiation to do their measurements. And by shifting to the infrared, they were able to use longer wavelengths that are able to go all the way through that gas and dust. So, problem one was what color of light do you need to use to see into the center of the galaxy? Now, problem two is our atmosphere is a noisy, moving thing.
Mm-hmm.
And light coming through our atmosphere is passing through pockets of variable temperature and other effects that cause that light to get refracted in variable ways as it travels that distance.
Right.
To compensate for that, what we often do is we use adaptive optics, which works to tilt tip different systems, flex different systems within the telescope to compensate for the motions of the atmosphere. That's fairly new technology. It's complicated technology, and it's not always good enough technology. The other way that we deal with this, and this is something even amateur astronomers do, is we take high speed images where each image is capturing the light as it passes through the atmosphere for one way the atmosphere is.
Mm-hmm.
The next one, the atmosphere is slightly different. So these two images will have moved relative to each other.
Yep.
But if you look at the brightest parts in both images, you can then line them up. So in this case, you find one of the brighter stars, multiple of the brighter objects within the image, and you use that to line up all of these high speed images. And then you can stack them and you can see things that you can't see in any one image,
Right.
but that are able to be seen in the cumulative stacked image.
I'll give just like a quick analogy. You know, when you look on the internet, you see these beautiful pictures of Mars and Jupiter and Saturn and stuff taken by
Mm-hmm.
amateurs. And the
Yeah.
way they do that is they point a video camera at a very bright object. This is the key. It has to be bright. And
Yes.
then they run the camera for an hour. And
Yeah.
then they feed every single video frame into a piece of software that then combines all of the images together and goes, well, there's a little part over here that looks good and a little part over there that looks good. And it just stacks and stacks and stacks. And as long as it maintains the integrity of the data, you get an entire view of the planet as if there's almost no atmosphere obscuring it from our point of view. And it's because you've got a lot of data, you can just keep matching, and the object was very bright. What makes this discovery so incredible is that viewing the stars at the center of the Milky Way in infrared, you do not have a bright object that you can look at.
You have bright enough objects to line things up,
Right.
but that's as good as it gets.
Yeah.
And they have literally spent decades now watching the motions of these stars, tracing them out, trying to get all the three-dimensional motions fully understood, combining spectra where possible. And they've built up a clear-cut case for the motions of these stars only being explainable with a black hole in the center
Right.
of these stars' motions. And it's always awesome to see two competing teams replicating each other's work using different telescopes and getting the same
Yeah.
answers, and then each focusing in on different
And
nuances.
that is nature. That is nature just telling you its secrets.
Hmm.
That two people, different, similar technique, different telescope, different hemispheres, seeing the same thing and arriving at the same conclusion. Beautiful. That's textbook. It's what you want. Nobel Prize is for everyone.
Exactly.
Yeah.
Exactly. Now, where this became a bit odd last week is Reinhard Genzel made a comment along the lines of he thinks that one of the reasons that they got the Nobel Prize this year was because the committee wanted to make sure there was more diversity in the awardees, and because Andrea Getz had been working on this work too, they both got the prize. And he pointed out some times when he was the one who got a prize and she was not. And that's just not cool, dude. You just got a Nobel Prize. Um,
Yeah.
so
Be
we are quite,
gracious.
yes. So I think he just had a poor moment. Don't do that, dude. Um, but these are two people that in general are very nice,
Right.
kind,
Right.
gracious people. And it's excellent to see them awarded for their excellent work. This is not the first award either of them have gotten. They've kind of been working through getting all the prizes forever. Andrea Getz, actually, she was one of the people who got early career awards back in the 90s when she was just starting her career. Um,
So you
they did
talked about
excellent work.
so you talked a bit about this idea that they use this technique to peer through the gas and dust of the Milky Way to
Hmm.
observe the stars moving, and what were they looking for?
So they were they were essentially looking to see, can we say the only object that can physically fit within the size of the orbits of these stars is a singular black hole? While it had been hinted at, thought, hoped, drawn on overheads that there was a monster called a black hole lurking in the centers of quasars and other active galaxies, we didn't have evidence of it through the 90s. And there were other arguments where people would say, well, maybe it's a swarm of stellar mass black holes. Maybe it's a swarm of white dwarfs. Maybe it's something else that we don't even know. And this is why people drew monsters in the center of black holes. Everyone had their own favorite monster to draw on overhead sheets.
Yeah.
With the work that Genzel and Getz did, they were able to identify motions of stars that were getting Pluto sized orbits around that supermassive black hole. And at that extremely small distance from the massive object, it became possible to say, we can't explain this as anything other than this amount of mass within this size radius,
Yep.
which seems to be consistent with a supermassive black hole, even though we can't see within the event horizon.
Right. So, um, just that, and I mean, it's hard to sort of do this as an audio podcast, and I'm sort of stumbling because the when you see the animations, the 16 years of careful observations that they made, you see these stars buzzing around this missing spot in space. I know we've talked
Mm-hmm.
about this before, but it is, if you had to watch like one of the most stunning pieces of observational work, this is one of them that you just can see these stars moving like comets around nothing. And
And
it can't be nothing. It has to be gravity.
and one of the things that really helped them early on is there's enough stars down near the center that they were able to catch one near its fastest point early on in this now couple decades long research program.
Yeah.
And by catching stars at their closest point to the supermassive black hole, they're able to get limits on both how big a thing could possibly fit in there, because clearly the star zipping by is not inside of it, and just how massive does it has to be? And this is just good old standard Kepler's motion with relativistic corrections of something goes fastest when it's closest to the
Yeah.
mass it's orbiting. And so they caught that. They caught that super fast zip on
Yep.
by
Yep.
before going out to linger at greater distances. And now they've done it multiple times. And it's just cool.
Yeah. And I think to finally, we're still waiting for the photographs taken by the Event Horizon telescope to bring the whole journey to home, right? That we will actually then see these interactions between the black hole, its event horizon, and the surrounding space, which has been predicted by Penrose. And that will sort of complete that phase of the journey to go from Einstein's idea to Penrose's detailed predictions of what should be seen to actual observations to powerful telescopes being able to actually reveal this region. It's just textbook. It really is. Like, this is Nobel Prizes. I'm so glad this was the Nobel Prize this year.
And black holes have a history of saying, okay, Nobel Prize for each stage of the work. We had Taylor, who in the past got a Nobel Prize for his discovery of binary systems that were radiating gravitational energy, which was assumed to be via gravitational waves. This is just black holes sometimes just keep revolutionizing how we see things and offering up more and more Nobel Prizes as they go.
Incredible. All right, Pamela, do you have some names for us this week?
I do. And as always, we are here thanks to the generous contributions of people like you. I we have a bunch of really awesome humans that work with us, and we like to provide them medical benefits if they need it and pay them a good wage for the work they do. And you make that possible. You're making the world better, people. You're making the world better.
Thank you.
So this week, I have a large list because we're getting to the end of the month.
Go fast.
I will. I will. So we have, I went too fast. We have Venkatesh Shari, Thomas Sepstrup, Joe Holstein, Sinai, Sylvan Vespi, William Andrews, Jeff Collins, Harold Bragenhagen, Ben Floss, Stephen Shewater, Merrick Vidarni, Arctic Fox, Nate Detweiler, Brian Gregory, Matt Rucker, Philip Walker, Ron Thorson, Kevin Nika, Elad Avron. I scrolled. Pardon, I scrolled. Elon Avron, Dave Lackey, Karthik Venkataraman, Cooper, GeForce 184, Antisaur, Keiko Seraph, Dean McDaniel, Paul D. Disney, Roland Vammerheim. Oh, my computer makes a mess when I scroll. I'm sorry.
Wow, that's a big list.
There is Chris Schreihofer, Jason Graham, Father Prax, Sarah Turnbull, Donald E. Mundus. And we're going to stop there.
Thank you, everybody.
Thank you.
All right, we'll see you next week, Pamela. All right.
See you next week. And Richard, please fix the spaces I injected awkwardly in those names.
All right,
Thank
I'm
you.
pressing stop and I'm saving.
Yep. Yep.
583. Export. Let's wave. Okay. Ben Kale is asking, hey, I just got Fraser's newsletter. How did he send it during the show? I sent it like a couple of hours ago. It just takes a long time for them all to go out.
Yes.
It takes a while for like 50,000 newsletters to go out. I'm not working on them by hand, each one.
So,
go ahead.
A Middleist says, if time slows down, the faster you travel. Then if you could travel close to the speed of light, would travel time to a distant star be reduced to the traveler's reference frame? Yes. In fact, to a photon, There is no time.
Hmm.
It's created and destroyed in the same moment, no matter how many billions of years it actually travels across the universe. And the faster you go, um, the slower you experience time relative to everyone
Hmm.
else. This is done really well in the movies Interstellar and Ender's Game. Um,
Well, for different
it's
reasons.
just
I mean,
cool.
Interstellar is done because you're close to a gravity well.
Yeah.
But if you hopped in your spaceship and you went like 99.9999999% the speed of light,
Hmm.
you could in your lifetime travel billions of light years. You could within a human lifetime get to a distance equivalent to the length of the observable universe. Like you would be 40 years older, but you could do it. But everybody else would be 14 billion years older. So, yeah, and we will eventually, we hope, experience this as we send spacecraft to other, once spacecraft are going 80% the speed of light, 90% the speed of light, we see the spacecraft slowly moving to its destination, but anyone on it, they experience 2 years instead of 4 years. So yeah, absolutely. John Drake asks, can eating satellite galaxies slow down a black hole's spin?
I would expect it to actually speed up as it gains angular momentum from what it consumed.
I mean, in
But it depends on the encounter.
right. So in theory, if you fed a black hole very carefully, you could slow it down by
Hmm.
feeding it material in the opposite direction of its spin. But most likely, you're going to be taking a lot of material. You're going to be adding its angular momentum to the black hole, and it's just going to spin it up and spin it up. Which is why black holes tend to spin very quickly. In some cases, close to the limits predicted by Einstein, when he wasn't specifically predicting the speed rotation rates of black holes.
Right.
Rich Wilson asks as a follow on, but don't photons slow down in some materials? So why don't they experience time then?
Um, so they're still going the speed of light. It's just the speed of light is variable in different materials. And time is consistent with that speed of light. So it has still stopped as far as the black hole is concerned. Not black hole, the photon is concerned.
Right. John Suffield is asking, what percentage of the mass of our galaxy is taken up by Sag A star? Not,
I don't know.
we can do the math. 4.1 million times the mass of the sun, and the mass of the Milky Way is 1.5 trillion times the mass of the sun. So, half of a percent,
Yeah.
like not much. People always imagine these black holes as the anchor of the galaxy, and they're not. Like if you removed the black hole from the center of the Milky Way would not care one iota. No one would notice. Oh, Slam RN is saying, isn't it amazing how small the Milky Way black hole is giving our size and how quiet it has been? It hasn't
So
been completely quiet.
it hasn't been completely quiet. It's we aren't in an active galaxy, and uh, based on the fact that it's not rotating quickly, we're probably never going to have jets. But there is evidence that it has released bursts of energy in the past when consuming who knows what. And this has shaped out shock waves that are visible in the X rays around the center of our galaxy, just various bubbles blown over time.
Right. The thing that is pretty interesting is that when material does fall into the black hole, it's
Hmm.
it's fairly easy for us to detect it. Even small amounts, like little blobs of gas falling into the black hole, will release a flash of X-rays that we can detect. And there was a blob that was falling towards the black hole that was going to encounter it. I forget the name of it. It was like G2 or something like that. And astronomers weren't even sure what it was as they were watching it. They thought like maybe it's gas, maybe it's a like some kind of maybe it's a star,
Yeah,
and I think it ended up behaving more like a blob of gas,
it was a
releasing about
blob of gas.
yeah.
Yeah.
And um but it's almost certain that Sagittarius star was a quasar in the past and will probably become one again in the future when we merge with Andromeda.
Just without jets. And that is fine.
Right. Corey S. says, I heard that Betelgeuse is closer than we thought. Could that mean that other calculations are different?
Oh yeah, and it was within error. So the when we make measurements in space, we say that something is, in this case, I don't remember what the numbers were, but it was like
It was 570 plus or minus like
so they
200.
previously thought it was like order of 2000 light years away.
Well, the most recent, like when we were talking about Betelgeuse maybe exploding, it was in the 570 range,
Okay.
580 range.
So whatever number they said they thought it was, it had an error bar on it where the best guess is this number, but we know it's actually could be out this far, could be this close.
Right.
And the new number they came up with was within the error bars and used a completely different way of measuring the distance. And when you have two completely different ways of measuring something, in one case using Hipparchus parallax measurements, which trying to measure the motion of a blobby object relative to background stars is
tricky.
kind of a furry mess.
Yeah.
The other method looked at what are the fundamental mode and first overtone mode of the star's pulsations. This is the equivalent of if you grab a soda bottle or another kind of bottle and you blow into it. The fundamental mode is that first note you get easily. The first overtone is when you increase the air going across it and you get that next pitch up. By looking at how the star pulsates in those two different modes, they were able to calculate essentially the resonance chamber of the star, the part that's pulsating, get the physical size of the star that indicated. And by knowing the physical size of the star and knowing how big it appears on the sky, they were able to calculate the distance. These two numbers from parallax and from physical size estimations were over each other's error bars, with the smaller number from the physical size being within the error bars of the other method. And it's a cool result.
Yeah, and because it's 25% closer than we thought, it means it's smaller than we thought, and also it means less likely that it's going to explode anytime soon.
Well, it's 100,000 light years off, at least.
100,000 years off.
No. Yes.
Yeah.
Yes. Yeah. Sorry.
Yeah. So
wrong unit came out.
Yeah. So it's not out to the orbit of Jupiter. It's out to the orbit of more than Mars. Like, it's still big, but it's just not quite as big. We've only got just a minute left. Can you shamelessly self-promote the upcoming Hangout-a-thon before we move on?
Yes, this weekend, starting tomorrow morning at 11 a.m. Eastern, 10 a.m. Central, 8 a.m. Pacific, 9 a.m. Mountain, just to say things out of order. Yeah. We are going live for a 36-hour-long stream. We are going to have guests. We're going to be building a full-scale model of the solar system in Minecraft. We're celebrating planets and raising money to keep CosmoQuest going. This is in honor of one of our community members, Paranor, Tim Hawkins, who passed away. And we hope you'll all show up. I'm going to be sending a complete schedule out to everyone who has subscribed to the CosmoQuest newsletter later today. All so go subscribe to our newsletter if you haven't already. Go to cosmoquest.org.
Perfect. All right. And thanks, everybody. And we'll see all of you next week. Or many of you tomorrow.
Yes.
So join us. Okay. Bye, Pamela.
Bye-bye.